next talk will be about exact Bayesian inference for loopy probabilistic programs using generating functions, presented to you by Lutz from Aachen University.
Good. Yeah. So my name is Lutz, and I'm presenting our current work at OOPSLA, which is called Exact Bayesian Inference for Loopy Probabilistic Programs. Of course, this is not only me, but joint work with my co-authors, one of whom's also sitting here. Yes. So why do we want to do probabilistic program analysis for Bayesian inference? That's one of the first questions. And let me bring up this following example. Just imagine that you're rolling a fair die until you have seen a 6. And in every roll, you observe that it was even. So it was 2, 4, or 6. And now I ask you, how many throws do you need on average to get the first 6? Observe that you have only made these even rolls. Maybe some of you can come up with a math for it and create the sigma algebra and think of random variables and expected values. But I think everyone in this room could just write a little program that specifically models the behavior I was just explaining. So first we initialize the two variables roll and the number of loop iterations C. And then we say, okay, until we hit the number 6, we uniformly sample, and we observe that the row was actually even, and then we count the number of iterations. And still we want to know how many throws do we need on average to get a 6. And now this question just transforms into what is the expected value of program variable C after termination. Okay, and there you can already see, just by doing probabilistic program analysis, we get a complete framework for making reasoning about stochastic processes, and we use probabilistic programs basically as a modeling language for these processes. Okay, yeah, that's what I just said. Here you can see a course overview of our approach. So on the left-hand side right here, you see a prior distribution. This is kind of, think of the input of a program or your initial belief about something. Then you have a loopy program with the conditioning statements. It just describes your stochastic model. And what we then do is we take this prior distribution and the model description, and if there occurs some while loops, we do some invariant techniques to reason about them, invariant-based. They can even have some kind of holes, which we call parameters, that also can automatically get synthesized. Then we compute the final distribution, or posterior also in Bayesian terms. And then once you got this posterior distribution, you can basically query all possible kinds of queries, like what is the expected value, what's the probability for certain events whatsoever. So because you once have computed the posterior distribution, you can then query it for whatever you want to know basically about your process. Okay, that brings me to the table of contents for my today's talk. And first, I want to give a brief recap about Bayesian inference and how we deal this with Bayesian inference encoding in EPGFs, which stands for extended probability generating functions. Then I will give a brief description about the semantics of our probabilistic program language, how we do the parameter synthesis and dealing with its while loops, showing some benchmarks, and in the end, give a conclusion. Okay, to get all of you on the same page, what is Bayesian inference again? So we recap. It's a method for statistical inference where we update the probability estimate of a hypothesis. Think of an input of our program. As we collect more evidence or information becomes available, as this distribution gets pushed through the program, basically, it updates and reforms its shape. And all of this is based on Bayes' theorem. And here you see the little ingredients on the right-hand side. P of theta, this is the initial belief, or think of the input distribution. Then we have the likelihood. This is basically the conditional distribution. conditioned you have seen this input, and you observe the data x given the parameter theta. And you have the posterior distribution. This one we are interested in computing. This is what our semantics actually does. And this P of x in the end is the marginal likelihood of the data, which is just a normalization constant. And this kind of reasoning allows us to continually update the beliefs as more data becomes available, or think of it, it allows us to transform initial distributions into posterior distributions in a compositional way throughout the program. Let me give you a quick example. Let's say we have a coin and we throw it 10 times. We want to estimate the number of the number of times that theta, lands heads out of these 10. And let's say our initial belief is that most likely when it's a fair coin, it should be roughly around 5. So we say it's maybe a Poisson distribution with parameter lambda is equal to 5. Then we do the actual experiment and observe 7 heads. So it may be not 100% sure that this is a fair coin. So we update our beliefs using the data we observed right here. So this was the prior distribution. This is here, this Poisson distribution with parameter lambda is centered here at 5. And then the update transforms this prior distribution into the posterior distribution. And you see how we retransform these shapes given by the actual model. And exactly this transformation is what happens when you compute the semantics of our probabilistic program for an initial parameter, initial distribution. Okay, how do we encode these distributions? Because it's not so easy to compute with pictures, right? And what we do is we, as I said, use extended probability generating functions. And this is a formal power series. And just think of infinite polynomial. And it has to satisfy certain properties. The first one is these coefficients right here, they have to be in the range of 0 and 1. And the sum over all of these coefficients must be between 0 and 1, so it encodes kind of the mass of a probability distribution. Okay, here's an example. Yeah, I think it's pretty clear. Throughout this talk, you will oftentimes see this is a bivariate extended probability generating function. But if we have something like x to the power of 0, we just omit it and say, this is the same as 1. So formally, this monomial is there, but we omit it. Okay, so let's dissect this a bit. So we have this formal indeterminates. This is a vector-valued indeterminate x. You can see it because it's bold-faced. And we have one specific indeterminate which denotes observation failures. So it might be the case that you roll a die and your program says we observe that the die roll was value 7, but the die has only 1 to 6 as possible values, right? So there is no probability mass which can satisfy this observation. This leads to an observation failure, right? Okay, then we have the exponent right here. And this one identifies the actual value of the program variables, or the state of the program. Here we have the probability that this state occurs, which is just a coefficient. And this is the probability, as I said, of the observation failure. Maybe we make this a bit more concrete. So here, let's say we have a geometric distribution in X. Of course, I cannot draw all infinitely many possibilities, so I truncated it. How would you translate this into a probability generating function? With probability 1/2, X has value 0. And probability 1/4, X is value 1. Plus with 1/8, X is value 2. I think it's clear how it continues, right? So it looks like this. And maybe the main point of doing this encoding is actually that for a lot of these sums which occur in discrete probabilities, we have closed forms. And we have just one fraction which allows us to reason over an infinite state distribution. That's the reason, amongst others, why we use ePGFs to represent these distributions. Okay, what kind of distributions can we, for example, represent? Like a Bernoulli distribution is the easiest one. a geometric distribution you have just seen, also uniform distributions or binomial distributions, even Poisson distributions have nice closed forms. The other properties are, for example, that once we have obtained such a closed form, it's very easy to extract important information like kth moments. We take the derivative and substitute these formal indeterminates with 1, or marginal distributions just by substituting operations. Stochastic independence we can check by marginalizing for the certain variables, and then see whether we take the product, whether we get back the joint probability. So there are very nice properties why we want to use this. If we want to, for example, know what the termination of a program is, we can just take the posterior distribution, substitute all values for 1, then we get the sum of all the coefficients. And all the coefficients encode all the possible probabilities for the states in which we end up with. So this gives us immediately the termination probability. Okay, how do we transform now these priors to posteriors? Let's make this first by means of an example. On the left-hand side, you see a program. And what I use is kind of these annotation style reasoning, for which I transform the initial distribution up to a final distribution. And right here, you always see a 2D graph, and the color plots basically the probability. Here you see the variable t, sorry, it's very, very little. And here the variable h. And for example, for t0 and h0, we have a probability of 0. For t0 and h1, we have a probability of 1. This exactly is encoded by this probability generating function, right? Okay, so first we do the if check. If h is 1, this is certainly fulfilled, so we actually don't do anything. Now what we do is we increase t by a geometric sample. So here we sample a geometrically distributed value with parameter 1/2, and we increase the program variable t by that value. So here's basically what happens. We have increased this t, so we first marginalized it out, and then we multiplied it by the closed form of the geometric function. This is what it looks like in the pictorially world. Then we set h to 0. So we just marginalize it out, and here is again the picture. Now we do the same for the else branch, but nothing actually fulfills the else branch right here. If h is not 1, then you don't get anything. So this is 0, but the program also does nothing, so it doesn't change. Right after it, we combine each branches, so this result and this result. And again, as the speaker before said, we don't do this in a case distinction, but we just sum them up. So this is the result. And now we do this observed term where we say we only want odd values of t. And this can also be easily represented right here. This is what we observe. So with probability 2/3, we will not satisfy this. And otherwise, this is our result. Okay, and in the final step, what we have to do is to renormalize it. And by which constant? Exactly 1 minus this constant. Because this is the probability which has to be normalized. And it basically, so the format doesn't change, but only the intensity of the color. Because, it's just a factor. Okay, here's the semantics of the program language. Don't look too much into detail, but the important things is that for the loop-free part, we basically preserve these closed forms of the probability generating functions. And also for the observed case, only the while loop can break this property, assuming we started with a closed form. How is the while loop actually implemented? Pretty standard as the least fixed point of a certain operator. And this basically mimics the equivalence of doing the while loop or unroll it one time and then do the while loop again, which is should be equivalent. So, but you saw these while loops, and how do we compute this fixed point? This is sometimes infeasible. And I already hinted to it a bit, that we use the invariant-based reasoning. The first thing is that we use invariance with Park induction. Maybe I just briefly recap Park induction. So assume we have such a while loop with the loop guard phi and the program P. Then the following holds basically, that the semantics of one loop iteration, or this invariant I captured in one loop iteration, if this is smaller than the semantics of I itself, we know that I over approximates the loop semantics. This is basically what Park's lemma states. And if we furthermore know that the program L is universally almost surely terminating, which means for every input, this program terminates with probability 1. We even have equality at hand. And this is what we make use of. So what we did is basically reasoning about the while loop. We boiled this down to reasoning about an invariant. Or about program equivalence, right? Here, this is basically, it means this program is equivalent to that program. So they produce the same output for any input. Okay, but this is actually decidable for loop-free programs if they are UAST. How do we do this? Let me give you a brief idea. So we have a loop and an invariant template. Here, this is the die roller, and this is our invariant template. We again write it just as a loop-free version. And we now want to show that if I take, so what we have to show is that they produce the same output on every input. And we can do this by the same trick. So as these probability generating functions, we're basically enumerating probabilities. We just lift this one step and now say, okay, second order probability generating functions enumerate probability distributions. So every coefficient is now not a probability, but a whole probability distribution. This is basically what is written here. And if we take one very particular one, which looks like this, so for every program variable, we introduce a new variable, a spurious variable, and this one tells you, or this special second order probability generating function basically enumerates all Dirac distributions, all point distributions. And there's a famous result about Katoen that if you know how the program behaves on every individual point in a discrete space, then you also know how it behaves on every possible discrete distribution just by convex combination. So we just have to test not for all inputs, but only for this one special input right here. And why does it work? Because syntactically, it's still just a formal power series. So my semantics works also for these kind of objects. Okay, so I had this loop. I had an invariant with some open parameters. Maybe I don't know them. And then I want to compute this. So the loop unrolling of this invariant here and the invariant itself, and compute this on this very specific input. And if those two things coincide, we know that they are actually this equivalent. And then by this Park's lemma, we know this is also equivalent to the while loop, and we can compute the actual posterior distribution. Yeah, this is what's written here again. So if we have two programs, they're equivalent exactly if they're equivalent on this one specific input, because it captures all possible ways the program can behave. Now in this case, you have to trust me or look in our paper. We can see that for these two things, it's exactly the same if we take for P the parameter value 2/3 and Q 3/4. And this can be automatically derived by a tool we have implemented. So it gives you these parameter instantiations for this. You just plug in some invariant template and it computes you these kind of things. Yeah, and this is then also decidable. Once you give me this invariant template and a loop, and I want to check, is there such a parameter instantiation, it's decidable. Okay, does it scale? So we have an implementation which does all these kind of things, and the answer for this is maybe. So first, let me say that this is the first program and first approach that is able to do this exact Bayesian inference for loopy programs. There are other ones which do not consider loops, and it works fine for them. For example, we will come to this, but this is the first one which can also handle loops, right? And here's a table which picks some benchmarks for our program, which is about programs which contain loops, so we cannot really compare it against some other technique. And what you can see right here is, so if we use our faster backend, because it's a Python implementation, most of them take less than 1 second, but even with computing these parameter instantiations. So at least it's a reasonable prototype. And if we compare to other tools which can do exact inference, like lambda psi or like Genfer, we can see that this is not our main thing we want to do, because we want to analyze loopy programs, but also for the loop-free ones, we are oftentimes reasonably well, sometimes even better, or can handle programs the other ones cannot, because of parameter instantiations or, So even in the loop-free case, we're not the best out there in the market, but we oftentimes can compete well. Basically this concludes my talk. So what we did is we introduced the PGF-based denotational semantics for these loopy probabilistic programs with flexible conditioning and while loops. We can deal with infinite support distributions, unbounded loops, conditioning and symbolic parameters. There is an implementation where you can play around with and try this out for yourself. So for Bayesian inference with conditioning, automatic invariance checking, parameter synthesis in invariance, and queries about the properties of output distributions can all be done in Prodigy. You can check it out. And basically, thanks for listening.
Thanks. So the time has run out, so maybe Martin can set up here, and we can take a very quick question.
Thanks for the talk. So it seems one component of the method is specifying the variant or the template. Oh, sorry, you can hear. It seems one method. First of all, thanks for the talk. One component of the technique is writing this loop invariant.
Yes.
Or rather, the template, and then you can learn the parameters.
Yes.
In practice, how difficult is it to find the right template, or are there thoughts about how you might automate the discovery of that template?
It depends. So usually it's not trivial, of course. But usually when you code up a while loop, I mean, some kind of invariant in mind why you do it this way, right? And this is also what you have to encode into this loop-free invariant. But of course, it's not an easy task. And in general, you cannot come up with an invariant automatically, because this is undecidable actually. But we have some future work which we're currently working on, which does not only parameter synthesis, but also is trying to synthesize invariants with a little different technique. Looks promising, but stay tuned.
And just very briefly, the second question is, can you handle nested loops, or do you have to sort of unroll them, to a single loop?
You can handle nested loops. You start with the inner one, do this equivalence thing, because once you know this is equivalent, for example, to such a loop-free code, you can literally substitute it in there, and then you only have, so you de-nest it basically, and you end up with one loop-free program, which basically does the same thing you want. Yeah.
Okay, thanks Lutz again for the wonderful talk, and we can take the discussion offline.